Building physical quantum hardware requires massive cryogenic infrastructure to maintain microscopic states against decoherence and thermal noise. Industry-standard classical simulators attempt to bypass this physical limitation by modeling qubits mathematically. However, these state vector systems must track a continuous probability field of 2 to the nth power complex amplitudes. This chart shows the exponential memory wall. Simulating just 50 qubits requires roughly 16 petabytes of RAM to store the resulting state vector. At the scale of millions of qubits, the memory requirements exceed the total number of atoms in the known universe. The Xylatic Toral processing platform, or XCTP, utilizes a chiral nested trilateral architecture to bypass these memory limits. This chart shows the XCTP linear scaling baseline compared to the legacy exponential curve. The engine simulates 10,000 qubits using 1.15 megabytes of RAM and 100,000 using 9.53 megabytes. A 1 million qubit benchmark resolved in 5.38 seconds, consuming 114.26 megabytes. The CNTA engine achieved these results using standard commercial data center silicon, executing the benchmark deterministically on a single standard CPU thread. The XCTP architecture avoids exponential memory growth by abandoning probabilistic complex amplitudes in favor of deterministic Toral geometry. This shift means the primary constraint for quantum computing is now the instruction cycle speed for involution folding rather than the availability of physical memory space. This geometric approach begins with a proprietary QASM to ZTC compiler. When standard Open QASM 3.0 circuits are submitted via the API, the compiler intercepts the code and explicitly bypasses all classical matrix multiplication. The compiler maps legacy quantum gates directly to their absolute structural topological equivalents on the Clifford torus. In traditional gate-based models, a Hadamard gate is used to create a state of superposition. The XCTP compiler instead maps the target vector onto the Heegaard boundary torus. This boundary sits at the 54.7% decoherence horizon. This horizon separates the integer sublattice, or D8, from the spinor coset, known as S+. Superposition is handled as explicit structural symmetry rather than a probability. The controlled NOT gate traditionally serves as the mechanism for quantum entanglement. In Zennoran Toral calculus, entanglement is a deterministic geometric lock. The gate translates to a sigma-29 spinor half-turn across the torus. This operation deterministically flips the target's chirality within a 24-cell incidence matrix. The remaining fundamental gates are resolved through similar lattice operations. A Pauli X triggers an instantaneous lattice negation across the origin, while a Pauli Z applies a conjugate phase rotation along the Mobius band. Measurement in this paradigm extracts 3.585 retained structural bits, while identifying the exact boundary where the remaining octonionic position bits are lost. Because quantum operations are mapped as discrete spatial geometry, the engine executes mathematical transformations rather than floating-point matrix multiplications. If the system is not tracking a massive complex density matrix, how is the state preserved in memory? Legacy simulators must store a continuous field of floating-point numbers to represent every possible state of the register. XCTP instead tracks the state using the signed state envelope. A single-node state is encapsulated by 4 absolute fixed parameters. These are the absolute index, its coordinate in the macro topology, and the fractional phase on the torus. The third parameter is the orbit step, the winding integer defining the depth of the Mobius cover. Finally, chirality is a simple binary indicator of positive or negative 1, denoting whether the state is classical or superpositional. Because the state is a definitive geometric coordinate rather than a probability matrix, the bandwidth and memory overhead per qubit remains flat. Replacing continuous probability matrices with discrete topological envelopes allows memory complexity to drop from O to the 2 to the n to O to the n. Scaling to millions of variables requires a method to resolve deep entanglement cascades without hitting local processing walls. XCTP utilizes a cyclonic recursive pump and trilateral stereoscopic resolution to achieve this. The architecture employs 3 nested lattice steps, E8 at level 0, Leech at level 1, and the 120-dimensional Crag lattice at level 2. System alpha, the forward mapping perspective, extracts a chiral orientation by projecting the level 0 state into the level 1 Leech lattice. Simultaneously, system beta performs a reverse mapping, projecting from level 1 out to the ultra-high precision Craig lattice. The stereoscopic Moray gate performs a deterministic interference check between these two distinct orientations. If the phases from system alpha and beta align within a structural tolerance, the state achieves a stereoscopic lock. This confirms the truth of the state without probabilistic decay. The final step of the pump is the Mobius inversion fold. This fold compresses the high-resolution boundary resolved at the Craig lattice and pushes it back to the foundational E8 base state. Feeding 120-dimensional topology recursively back into an 8-dimensional root brackets the search space, achieving a 3.85x reduction in mathematical operations and eliminating circuit depth decoherence. The XCTP architecture has exceeded the state vector memory wall and the flat lattice processing limit. While tensor network models fail when global entanglement entropy climbs in deep circuits, Toral geometry remains stable. This chart shows the XCTP engine maintaining linear execution bounds during a hardware-efficient ansatz benchmark, even under continuous phase rotations across 100,000 qubits. Linear O of n scaling allows for the deployment of quantum logic across specialized enterprise domains. One such application is edge-deployed quantum machine learning. Because a 10,000-parameter quantum neural network circuit requires only 1.15 megabytes of RAM, complex models can run natively on embedded hardware without cloud connectivity. In topological data analysis, the engine maps 500,000 data points to directional D8 integer roots and holistic S+ spinor roots. Resolving these through stereoscopic collapse allows the system to identify persistent shapes and voids across the entire dataset simultaneously. For post-quantum cryptography, the recursive Craig to E8 pump replaces the matrix-heavy quantum Fourier transform. By extracting geometric periodicity from 50,000 entangled bounds, the engine provides the discrete phase components required for period finding. These exascale operations occur on standard data center racks, bypassing the physical constraints of cryogenic hardware. Translating the phenomenological approximations of quantum physics back into exact Toral geometry resolves thermal noise and exponential memory constraints, rendering quantum logic as a robust classical data structure.